A very happy day and welcome back to yet another video on bipolar junction transistors. In our previous video lectures, we had understood the different regions of a bipolar junction transistor. We also differentiated the regions based on area and the doping level. We also understood that there are two junctions that will be formed when a transistor is constricted using two back-to-back diodes. One being the emitter-base junction, the other collector-base junction. In one of our lectures, we had discussed about the behavior of a bipolar junction transistor under unbiased condition. We also came to know that an unbiased transistor is of no use in actual practice. So we need to go for biasing. Biasing is the application of an external DC supply across the terminals. You apply external DC voltage across the emitter base terminal and the collector base terminal. So in this lecture, the learning objectives would be to outline the working principle of a transistor under biased condition. After application of the external DC supply, we are trying to understand the behavior of the bipolar junction transistor. In the process, now we will try to determine the current components of the transistor. Now before moving on with the lecture, we will make a few things clear. We know that there are three regions in a transistor: emitter, base and collector. Emitter has a larger area and doping is very high. Base has a very thin area and the doping is also going to be very light. Collector has the largest area and the doping is going to be moderate. We will have this concept in mind. The second concept that we will keep in mind is flow of electrons is what we call it as current. But the direction of the conventional current is always opposite to the direction of the electron current. Say for example, if there is an electron here and if the electron flows in this direction, the conventional flow of current is always taken opposite to this electron flow, which means that the conventional flow of current is in this direction. Having these two things in mind, now we will try to get into understanding the working principle of an NPN transistor. For simplicity, for clarity, we do take NPN transistor. We can also take PNP transistor. So these are the three regions: emitter, base and collector. And this picture will substantiate the concepts that we have taken here. Highly doped, very lightly doped, and this is moderately doped. As you could see, the electrons present moderately. We have reverse biased the output terminals. The collector emitter terminals is given a reverse bias here. And how do you say that it is a reverse bias? The collector, which is an N-type semiconductor, is connected to the positive polarity of the battery and the emitter is connected to the negative polarity of the battery. And what would happen automatically? Now you will have a change in the depletion layer. You could notice that the depletion layer of the collector base junction widens because of the reverse bias that is given over here, and you have another depletion region formed which is in the emitter base junction. And when you compare these two depletion layers, the depletion layer of the emitter base junction is smaller than the depletion layer in the collector base junction. So when you talk about the voltage drop across the emitter and collector terminals is denoted by VCE, voltage drop across the collector emitter terminals, which will be equal to the voltage drops across these junctions, right? The voltage drop across the base emitter terminal is taken to be VBE, voltage drop across base emitter terminals, and voltage drop across collector base terminals is denoted by VCB. As indicated earlier, voltage drop across the collector emitter terminals is the summation of the voltage drop across the base emitter junction and the collector base junction. Now what we have done here is we have forward biased the input terminals. The base, being a p-type semiconductor, is connected to the positive polarity of the battery or DC supply, and the emitter, which is an n-type semiconductor, is connected to the negative polarity of the battery. So this forms a forward bias across the input terminals. We will now investigate what really happens after giving this forward bias. When the forward bias exceeds 0.7 volts, which is nothing but the barrier potential of silicon, the electrons flow towards the base region. This concept we have already understood when we discussed forward biasing a diode. Now once the forward bias exceeds the knee voltage or the cut-in voltage, the electrons are pushed towards the base region and the electrons start flowing towards the base region. Now we will bring in this doping and area concept inside of the base. The base has a very thin area and the doping is going to be very light. As the doping is very light, there are not going to be sufficient holes inside. And as the area is going to be very thin, the electrons that would come to the base will have a lesser distance to traverse from the base to the collector. They do have a very small distance to travel. They come here, they become minority carriers, and they do not have enough holes to recombine. Only few electrons recombine with the holes that are present in the base, and the remaining electrons are pushed towards the collector region because they get attracted by the positive terminal over here. And we have already known a concept for majority carrier. Crossing a depletion region is like climbing a hill, a man climbing a hill. This is for majority carriers. Whereas for minority carriers, crossing a depletion layer is like moving down the slide. A child moving down the slide, it becomes very easy. And so the electrons which form the minority carriers in the base, they slide down very easily through this depletion layer and come to the collector. Now note the difference. Here there was a moderate number of electrons present in the collector region. After application of bias, the number of electrons in the collector region increases. We will now try to bring in the direction of flow of current here, so that now we will try to understand the different current components of a NPN transistor. Now we have seen the working principle of a NPN transistor. Now we will see what are the different current components that are going to be available. Now after application of the bias, the forward bias exceeds 0.7 volts, the electrons move or rather flow from the emitter to the base. So the flow of electrons is going to be in this direction, and so the conventional current is going to be opposite to this electron flow, and so the direction of the emitter current is in this direction. From here, now after electrons recombine, they get attracted towards this positive polarity, and so electrons will move in this direction, and so the conventional current is taken opposite to the electron flow, and so the conventional flow is taken in this direction, and we name it as the base current. So electrons would flow, they get attracted towards this positive polarity, and so they move in this direction. The conventional current is going to be in this direction, now which is called as the collector current. There are two currents that are moving into the terminals, base current and the collector current. They move into the terminals, whereas the emitter current moves out of the terminal. As per KCL, the Kirchhoff's current law, you could write the equation to be IE is equal to IC plus IB. the current that is going to flow out of the terminal is equal to the sum of currents that are entering the terminals. So IC and IB. So this is about the current components of a bipolar junction transistor. So we have just talked about the current components of a transistor in majority carrier perspective. There are current components because of the minority carriers, and that we will take it up in our later videos. Now, to just have a summary of what we have seen, we have understood the working principle of an NPN transistor, and we have also determined the current components of a transistor. To just have a recap, the input terminals are forward biased and the output terminals are reverse biased, which means that we have made to work this transistor under forward active mode. So during forward bias, when the forward bias exceeds 0.7 volts, the electrons are pushed from the emitter to the base. That constitute the emitter current. Electrons become minority carriers inside the base, and few electrons recombine with few holes in the base. Out of the electrons that come into the base, only few electrons will combine with few holes in the base, right? Because only few holes are going to be present. So only those holes can combine with the electrons, and these electrons get attracted to towards the positive polarity of the forward bias that is given, and that constitute the base current. And during reverse bias, the electrons in the base are attracted by the reverse bias, right? The minority carriers. So there is one more reason to quote. The electrons in the base are minority carriers. They slide down through this depletion layer and come into the collector region. So electrons in the base are attracted by the reverse bias, and this constitutes the collector current. And from these concepts, we have determined the current components of the bipolar junction transistor, and we write the equation to be IE is equal to IC plus IB. Hope you have understood the working principle of an NPN transistor. If you really like this video, click the like button, post your comments and subscribe this channel. Thanks for watching this video. We will meet again in another interesting video. Thank you so much.